All right, so welcome to our recitation session 2. All right, yeah, so I'm taking this from home, and it's raining very heavily with a thunderstorm outside here. All right, so yeah, so you might hear a lot of background noise, and also if I ever get disconnected or anything, just stay on the call. All right, I will join back in. All right, quickly. All right, so yeah, so I'm nearing the end, okay, of the semester, the module. All right, so there's only two major topics. Okay, one is on the pipelining, and the other will be on the cache design. Yeah, so both are not very new in a sense. Carrying on from, especially the pipelining, sort of carrying on from where we left off with MIPS. Okay, so the cache may be a bit new, but it's still making use of many of the concepts we learned before, okay, in terms of logic circuits and design and so on. All right, so let's come to our session for today. Let me share screen and then we can get started. Okay. All right, so I will go straight to the quiz questions. Okay, so I think once we go through the quiz, as always, we will sort of, in a sense, recap the things that are also covered in the lecture material. All right, so in the first question, we are given this truth table where we have the current state AB, the input X, and then the next state A plus B plus and Y. All right, and so in a sense we can break up this table into two halves. Correct, one is the input side, okay, and the other is the next state and output side. Okay, and what we are asked to do is we are asked to specify or come up with the expression if you were to use T flip-flops. Okay, T flip-flops to implement the sequential circuit. Okay, so let's look at this step by step. All right, so if you've already gone through the material, you'll see that actually all of this is in a sense very procedural. Right, as long as you understand step 1, step 2, step 3, and so on. Okay, you understand the steps involved and you know how to use the excitation table of the different type of flip-flops, then it is just procedural. Okay, nothing really I would say tricky in a sense. Okay, do we need to memorize all behaviors? Okay, so you don't need to memorize any of these excitation tables or behaviors. Okay, the exam will most likely be open book. Okay, in a sense, very similar to the midterm that you had. All right, so you can refer back to your notes. Okay, so I think yeah, as long as you know, probably you just have a summary table of all the excitation relationship. Okay, then I think that will be easy to refer to. Okay, so let's look at the T flip-flop. So for T flip-flop, just to quickly summarize, if you look at T, okay, and the Q of T plus 1, okay, the relationship is as long as T is 0 means there is no change. Okay, T is 1 means the output will toggle. All right, so as long as we know this, then it's easy to extend this. Okay, so let me extend this here. Okay, so we have TA and TB. So for A, basically we look at the relationship between, for TA we look at the relationship between A and A plus. All right, so we see that the first entry is 0 and 1. So 0 to 1 is a toggle, so this must be a 1. Okay, 0 to 0 is no change, so 0. 0 to 1 is a toggle, so it's a 1. Okay, 0 to 0 is no change, so it's a 0. 1 to 0 is a toggle, so it's a 1. 1 to 1 is no change. 1 to 0 is toggle, and 1 to 1 is no change. Okay, so that is based on the excitation table here. Okay, that how a T flip-flop will behave. Okay, when the T is either 0 or 1. Okay, so as before, I'll continue. All right, if you have questions, you can just put in the chat or you can ask me. So for TB, we look at the relationship between B and B plus. So 0 to 1 is a toggle. So TB must be 1. 0 to 0 is no change. Okay, 1 to 0 is a toggle. 1 to 1 is no change. 0 to 0 is no change. 0 to 1 is a toggle. 1 to 1 is no change. And 1 to 0 is a toggle. Okay, so that is basically the first step always, right? Depending on the question, what flip-flop they ask you to use, you look at this excitation table, and then from there you look at the relationship between each input to the next state. That means A to A plus, B to B plus, and so on. Okay, so once you get this, then the rest is just coming out with the K-maps for the simplified expressions for each of them. All right, so let's draw the K-map. Okay, so I'll first do for TA. So we have A, B, and X. So 0, 1, 0, 0, 0, 1, 1, 0. Okay, so I'm going to put in all the values. Okay, so directly take the TA inputs and put it here. This is 1, 0, 1, 0, then 1, 0, 1, 0. Okay, so by grouping this and this, we get that TA is equals to X bar. All right, so that should be the result for TA, and then we do the same thing for TB, and then finally for Y. Okay, so if you see, they are all the exact same steps that you saw in your lecture slides. Okay, there is nothing new or different here. Okay, the same steps, only thing is 1, 0, 1, 0, 0. Yeah, so the only thing is the flip-flop that you asked to use, that's all. Other than that, everything is the same. All right, so here we can group this two and we can group this two. So you get TB is AX plus A bar X bar. Okay, and finally for the Y, okay, so we have 1, 0, 0, 0, 1, 0, 0, 1. Okay, so again by grouping this and this, you get Y is B bar X bar plus ABX. Okay, so I think this is should be doable, all right, based on whatever that you have covered in your slides, all right. So again, from A, for each current state and the input, we get the next state. Okay, or in this case, it's already given to us. So from there, we decide, or based on whichever flip-flop we are asked to use, we use the excitation table and come up with the flip-flop inputs. All right, and that will give us this required expression for each of the inputs of the flip-flop. Okay, so in the next part here, we are asked to do the same thing, except that we are going to use the JK flip-flop. Okay, so other than the excitation table, all right, I mean, we start with the excitation table. So let's do that first. So we have Q, Q plus, and JK. So we have 0, 0, 0, 1, 1, 0, 1, and this will be 0x, 1x, x1, and x0. Okay, so with that, you can then go ahead to extend this. Okay, so I'll have JA, KA, GB, KB. Okay, so we'll do the same thing as before. So we look at current state and next state. So A, to go from 0 to 1, okay, you just follow this excitation table here. So 0 to 1 is 1x, all right. Then 0 to 0 is no change. Okay, so it'll be 0x. Then 0 to 1 is 1x. Okay, 0 to 0 is 0x. Okay, 1 to 0 is x1. 1 to 1 is x0. 1 to 0 is x1, and finally 1 to 1 is x0. Okay, and then for B to B plus, we do the same thing. B 0 to 1 is 1x. Okay, so 0 to 0 is 0x. 1 to 0 is x1. Then 1 to 1 is x0. And 0 to 0 is 0x. 0 to 1 is 1x. 1 to 1 is x0. And finally 1 to 1 is x1. All right, then the rest is as before. We're going to have 4 K-maps, okay, to get the expression. Okay, so this will be JA. So A, B, X, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. So I'll just directly fill in here. 1. Okay, so by grouping this and this, we'll get JA is equals to X bar. Okay, then the next one, AA 0, 0, 1, 1, 1, 1, 0. So here we have X, 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 1, 0, 0, 1. Okay, and then I group it here. I'll get KA is equals to X bar. Okay, and then I do the same thing for JB and KB. This is JB and KB. A, B, C. Okay, so for JB, it will be 1, 0, X, X, then 0, 1, X, X. And for KB, here will be X, X, 1, 0, and X, X, 0, 1. Okay, so by grouping here, we can get this and this. So you get GB is A bar X bar plus AX, and here you get this and this. So KB is A bar X bar plus AX. Okay, so it has X here. Yeah, so if you notice, this is actually another way of expressing the XNOR operation. So this is A XNOR of X. Same thing over here. A XNOR of X. Okay, so that is basically your A and or the same thing. All right, only thing we are using JK flip-flops. Okay, instead of T flip-flops. Okay, but the process steps are all the same. Okay, so I think this one should be fine. Okay, I don't think you should have much questions. All right, it's the same process as your lecture slides. All right, so that's how you get the answer there. Okay, so next is this circuit over here, and we are asked to explain this behavior. Okay, so how do we go about doing this? Okay, so let me move it up here a bit. Okay, so this is a circuit. Okay, so we are asked to express the behavior. So the way we can express the behavior of a circuit is when we get the state transition diagram. Okay, we get the state transition diagram. So in order for us to get the state transition diagram, we first need to sort of work step by step. So the first thing is we need to know what are the expressions that relate that will trigger the inputs here, the S and R here, okay, for both flip-flop A and flip-flop B. Okay, so once we get the expression, okay, that means we are going to work backwards from the earlier question. Okay, so that means what you're doing is over here, you're going to work backwards. Okay, that means we are first going to come up with all this expression. Okay, so instead of J and K, we're going to come up with the S and R expressions. Then from those S and R expressions, you'll be able to know from the current state, okay, what will be the input, what will be the next state. Okay, and then with that understanding of the current state and next state, we can draw the state transition diagram. Okay, once you draw the state transition diagram, you'll be able to understand how the circuit is going to behave. Okay, so the earlier question is in one direction, this is the reverse direction. Okay, so let's first understand, okay, this relationship, okay, of the SR inputs. So here we have an input X. Okay, so from input X, we have a pass-through or NOT gate. So this will be X bar. Okay, and this line, the second input is connected to Q. So we'll call this, so this Q is actually the B output. All right, so in a sense, to make it easier, instead of calling it Q and Q bar, you can just call this as A and A bar, and we call this B and B bar. All right, so the second input is actually connected to B. So this is X bar B. Okay, so for SA, so we can write it here already. SA is equals to X bar B. All right, for the other AND gate, one input is X, all right, which is this line over here. The second input is connected to the B bar. Okay, B bar. So this is X B bar. So your RA is equals to X B bar. Okay, so for the B latch, SR latch here, we can see that S is connected, or both connected to OR gate, and in turn, earlier to that is two AND gates. Okay, so we need to trace the input. So this will be your X bar, okay, coming from here. and this second input is connected to the B bar. So this is B bar, and also connected here, B bar. Okay, and this second input for this AND gate is connected all the way back to A. So this is your A. All right, that means this S over here, SB, is the OR of two terms, right? The first term is X bar B bar, X bar B bar, or with A B bar. Okay. Now for the second OR gate, which is RB, okay, the two inputs. Okay, so the first AND gate, okay, this first input is connected all the way back to A bar. So this is your A bar over here. All right, and this second line here is connected all the way to B. So this is your B, which is also connected here, B, and the second input here is connected to X. Okay, so your RB is actually the OR of two terms. One is your A bar B, the other one is XB. Okay, so that is the first step, coming up with the expressions for the inputs to the flip-flops. Okay, anybody has any doubts on this? Okay, so this part is just yeah, you just need to be careful. All right, you don't crisscross any of the lines, and you trace the lines correctly. So as long as you put a pencil or use a pen to sort of trace the line, then you should be able to look at exactly where it's connected to. All right, so that is those are your expressions, okay, for the SR inputs. Okay, now once you have these expressions, we can come up with the table. All right, so the table will have this current present state, okay, which is your A and B. Then you have your input, which is your X, okay, and then we have your next state, which is your A plus and your B plus. Okay, and then over at the output side, you have your triggers or your inputs for your flip-flops, which is your SA, RA, and your SB and RB. All right, so those are all the inputs. Okay, so let me draw all the lines here. Okay, so let's do it step by step. So the first inputs here will be, so we can go through all the possible values. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay, so in terms of inputs and the present state, these are all the combinations. Correct? So what we need to do now is, now the next state we cannot know yet, but what we know is we know the how the present state and input values are used in the S and R of both the flip-flops. Okay, so what we need to do is we now need to apply these expressions, okay, to the inputs over here. Okay, so let me so this is the first one. Okay, so I'm going to go through some of it, and the rest I think you can follow through. Now let's look at the first one. Okay, so the way you analyze is you take the current AB values and input values to determine what should be the S and R values for both flip-flops. Okay, so if I take at SA for example, so this will be X bar B. So X bar B will be, X bar will be 1, and with 0 will be 0. All right. Similarly here, X bar B. So 1 X bar will come 0, 0 and with 0 will be 0. Okay. If I take this third line here, X is 0, so X bar will be 1, and B is 1, so that will be give me a 1, and with 1 will give me a 1. All right, so you go through the entire sequence step by step. That means for each entry, you need to go back to the expression here, look at what are the values of X or X bar and B or whatever, and then fill in the respective S and R values accordingly. Okay, so I already did that, so I'll just put in the numbers here. Okay, so these are all the values you will get. Okay, so I'll not go through each and every one. Okay, it will take a while. Okay, so I think I just, as long as you understand what you're supposed to do, I think you should be fine. If anybody is not clear how I get these values, you can let me know. All right, like I said, what you need to do is, like for example, RA is X B bar. So for every entry here, you look at what is the X value, 0, and with B bar. So 0 and with 1 will give me a 0. Okay, so the next entry, X is 1, B is 0, so B bar is 1. So 1 and with 1 will give me a 1. All right, so that is how you fill up all these values. For A is a bit easier, but B is a bit more complicated because you need to look at two possible scenarios. All right, one is XB combination, the other is AB combination. Okay, so for example, SB over here is either X bar, B bar. So since X bar, B bar is 0, so X bar is 1, B bar is 1, so that AND operation will already give me a 1. Okay, so since it's all operation, as long as either one is a 1, the output is going to be a 1. All right, if I take the next entry, X is 1, so X bar, B bar will be 0, then A, B bar, so A is also 0, so the outcome is also 0 here. All right, so you need to again go through line by line to figure out all these values, okay, based on the expression you have. Okay, then this is 0, 0, 1, 1, 0, 0, 1. Okay, so now you have this already. All right, that means you know the present state and the input, and then you know the SR values for each input combination, okay, with the present state. Okay, now we can come up with this next state. Okay, we come up with the next state. Okay, so that will be based on the excitation table of the SR. Okay, so for SR flip-flop, we know that the next state values will be 0, 0. So this will be QT, this will be 0 and 1, and this is undefined. All right. So with that, we can say what will be the next state value. So if I take, for example, A currently is 0, and my SR is both 0, 0. Okay, which means it will be a no change. So it will be 0. Okay, if my current state A is 0 here, okay, and my next state is 0, again it is 0 here. If I'm 0 here and my current SARA is 1, 0, all right, then it will be a 1. Okay, so you can see that based on the present state, okay, SR, based on the SR values, all right, I'll be able to know what will be the next state. Okay, so if it's 0, 0, then it is no change. So 0 is 0, and so on. Okay, so I need to fill up this based on the SR values and the present state. Okay, so I'll get all of these values here. This will be 1 0 0 0 1 1 1 0. Okay, so for B plus, you look at the current B value and the SBRB. Okay, so any questions on how we fill up this next state table? Okay, so it is again based on the excitation table. Okay, and then we look at the present state and the current SR values to know what is the next state. Okay, so once you have all of this, then the last step, okay, is actually to come up with the state transition diagram. Okay, so let's do that now. So we can say that my first state here is going to be 0 0. Okay, and if my current state is 0 0, okay, which is here, my next state will become 0 1 if my input is 0. Okay, my input is 0, it will be 0 1. So from 0 0, if my input is 0, I'll transition to 0 1, the state 0 1. Okay, if my current state is 0 0 and my input is a 1, then I will stay in 0 0. Okay, so my input is a 1, I'll stay in state 0 0. All right, so that is how you draw the state transition diagram. So now I'm in state 1, correct? So if I'm in state 1, and my input is a 0, I will transition to state 2. Okay, I'll transition to state 2. So my input is a 0. I'll transition to state 2. If I'm in currently state 2, okay, sorry, state 1, and my input is a 1, I will go back to state 0. Okay, so I'm currently in state 1 and my input happens to be a 1, I'll go back to state 0. Okay, now the next one, I'm in state 2 now. So if I'm in state 2 and my input is a 0, I will transition to state 3. Okay, so if I'm in state 2 and my input is a 0, I will transition to state 3. And if I'm in state 2 and my input is a 1, I will go to state 1. So from state 2, I'll go back to state 1 if my input is a 1. Okay, and finally, if I'm in state 3 and my input is a 0, I will stay in state 3. Okay, so if I'm in state 3 and my input is a 0, I will stay in state 3. Okay, and if I'm in state 3 and my input is a 1, I will go to state 2. So my input is a 1, I'll go to state 2. Okay, so that is basically your state transition diagram. Okay, so you can imagine that right now, if I would analyze this, if I say my x is 0 and I'm starting from state 0, and if I keep clocking it from state 0, I'll go to state 1. Then from state 1, I'll go to state 2. From state 2, I'll go to state 3. And from state 3, I'll just stay in state 3 indefinitely. All right, that means if my x is 0, I keep counting up until I hit state 3, and then I just cycle that. Okay, if I have x equals to 1, all right, and if I'm currently in state 3, then I will go to state 2, then go to state 1, then go to state 0, and then continue in state 0. Okay, so basically x is 0 is counting up. So this is to count up and this is to count down. Okay, only thing is when you count up, you count all the way until 3 and then you just stay there. When you count down to 0 and then you just stay there. All right, so it is quite a lengthy process. All right, but like I said earlier, it's procedural. Right, it's procedural. It's nothing out of the blue or anything like that. It's just you just need to be very careful with the ones and zeros and all these tables you need to fill in. All right, and then you'll be able to analyze it. All right, so again, you can never figure it out from looking at this. Correct? When you look at this, there's no way for any of us to know how the circuit is going to behave. Or it's impossible. Only when you go through the whole process of translating, coming up with the expressions, then coming up with a table, then filling up the next state, and then from the next state, okay, filling up this state transition, then you are able to have a clear understanding of what that circuit was trying to do. Okay, but you have to go through that process. Okay, then only you come to this state transition diagram, and then you are able to say exactly what you are trying to do. Okay, so any questions on this? Okay, so there's a question. When x equals 0, if current state is 0, we follow the sequence. For current, is it possible for current state to be 3? Okay, so okay, to put it clearly, practically speaking, when you power up any circuit, you cannot guarantee a default state. Okay, so that is why if you look at most of your combinational circuits or your sequential circuits, there is usually a reset line. All right, there is usually a reset line to bring everything to a preset starting point. Okay, but if let's say I just take the circuit as it is, and there is, let's say, no reset line, correct? So when I power up the circuit, okay, each time I power up, it may actually have a different starting point. Okay, that's the truth. That's the truth. Because you can never predict exactly how all the different signals will stabilize that will eventually trigger the flip-flops and give you one initial starting point. Okay. So assuming you don't have a reset line, that means when I first power up the circuit, it could be anywhere. That means it could be in state 2, or it could be in state 3, or it could be in state 1. Okay, but what we do know is that doesn't matter, in a sense that the moment the first trigger comes in, the first clock comes in, all right, I will go from the next current state to the next state depending on my x value. So if let's say I happen to reset and I happen to start in state 1, it's fine. Okay, that means when the clock comes in, if I'm 0, I'll go to state 2. Okay, if x is 1, I'll go back to state 0. Okay, so regardless of where I start, it will still go in the same sequence. That means you either go up and stop or circle at 3, or will go count down and circle at 0, depending on the x value. Okay, so no other questions. Okay, so in terms of the quiz, that's what we have. Okay, so we'll go through the Slido questions and then the extra practice questions. Okay, so QT plus 1, Q plus, and Q bar really mean the same thing. Okay, so QT plus 1 is basically the next state. Okay, so generally we can say that this and this refer to the same thing. Okay, because qt plus 1 means what is the next q value, which is also q plus, which is the next state. Okay, but q bar, okay, is different. Q bar is the opposite of q. That means if you look at any flip-flop, okay, there's always a q and a q bar. Okay, so the q and the q bar is basically the current output and the inverted output. Okay, so it's not the same as q plus, which is the next state. So why is there a circle at the q bar? So that circle is always, so in digital system, the circle is always signifying the inverted or active low input or output. Okay, so it's just like, for example, if I have an AND gate here. Okay, so this is actually equivalent to what? It's actually equivalent to an AND gate with a NOT gate. All right, that means we're saying that the current output are inverting. All right, now it's the same thing as me if I were to draw something like this. Okay, so this is equivalent to saying I have two active low inputs, okay, to trigger an output. So this is equivalent to saying that I draw something like this. Okay, which means that if you think of it, for an AND gate, when all the inputs are a 1, then the output is supposed to be a 1, correct? But if I say it's active low, means when all the inputs are 0, then output will be a 1. Because when it's a 0 here, I'll flip it, then it will become a 1. So it sort of signifies the active state. So the Q bar and the Q is basically telling you that one is the active high output, the other is active low output. That means the inverted version of it. Okay. So in slide 17, how is JA, B, and KA, B bar? I think this is the slide. So it's all about how the circuit is connected, right? So if you see here, for JA, it is connected here. And this is the B output. Right? This is the second flip-flop, which is the B output. So JA is actually connected directly to B. Okay, whereas KA, which is this, is connected back to the Q bar. So this is the Q bar, which is representing B. So this is actually B bar. Okay, so that is how we come up with this expression here. Okay, so I hope that sort of clears up those questions. For flip-flop, is there a reason to choose either falling edge or rising edge? Okay, so generally for falling edge or rising edge, there is no particular reason to choose one over the other. Basically, as long as all your circuits are going to trigger on the same edge, then everything will cascade based on that same event. Okay, so when the clock, let's say if all your components are, let's say, positive edge or negative edge, so when the negative edge triggers, then it will trigger all the associated circuits to take action based on the current input and the current state to give you a new output. Okay, so next question is latch. Okay, latch and flip-flop. All right, so in a sense, what's the difference? If you are wanting a circuit to trigger based on the event being captured, or as long as the event is happening. Okay, so to take a simple example, okay, let's assume that I have a switch. Okay, so okay, let's not complicate it. Let's make it a simple switch. Okay, so imagine that right now, when I close this switch, I want to keep track of a counter. Okay, so whenever I close the switch, it counts from 000 to 001 or 010 thing. Okay, so if my aim is every time I press the switch, I want to increment by 1. Okay, every time I press the switch on increment by 1, then I can design a circuit such that, okay, I wait for the trigger. Okay, whenever I press, okay, I generate a positive or negative transition, then it keeps incrementing. All right. But if let's say the same scenario is the same switch, but instead of counting the number of times I press, I want to know how long I have pressed. Correct? I want to know how long I have pressed. That means I want to capture the moment the user press till the moment the user release. All right, so I'm interested in capturing this entire duration. Then I will use a latch. But I'll use a latch so that I will trigger my circuit the moment the signal goes to either high or low, and the circuit will continue to be active as long as that switch is pressed. Okay, so in a practical sense, that is the scenario, right? It all depends on what are you using or building this circuit for. What do you want to capture? Okay, do you want to capture events based on a trigger point, or you want to capture some duration where this event is happening? Okay, so this is like an example I can give you where you might choose one over the other, okay, depending on the event or what is the real world application of the circuit you're building. Okay, I think this also answers this question, the difference between latch and flip-flop. Okay, the latch is triggered to an active state. Okay, so if I say that my latch is active high enable, then while it is enabled, it will continue to work. Whereas flip-flop is always clock triggered. That means when the clock, active clock trigger the system, then it will take everything that it have, it will take the current input and the current state to generate the next state and the new output. Whereas in a latch based circuit, as long as the latch is active, it will generate a new input, okay, or keep updating the input if and when necessary. Okay, so for example here, all right, if I have a SR latch, which is in a sense gated, or if I enable, so this enable sort of acts as a latch. Right? That means as long as my enable is the active state, this is my enable line, during this entire duration, okay, my output Q can keep changing. Okay, output Q can keep changing during this entire time while the latch is enabled. Okay, whereas if this was a clock-based circuit, okay, so if it's a positive edge, that means only at this instance of time, I would have captured what is the SR value to trigger a new output, and that's all. Nothing else would matter again until the next positive edge, okay, of the clock. Okay, so again, I mean, there is no, how to say, no fixed cause to say that one flip-flop is better than the other or so on. It all a matter of maybe some circuit considerations, some design considerations, and maybe whether you want to make it simpler or easier or more cheaper and so on. Okay, so it's no particular, I mean, as you have seen in the earlier question as well, the same truth table, okay, you can design it with T flip-flop, you can use D flip-flop, you can use JK flip-flop, and all will work equally well. So there is no difference in terms of the logic or the implementation. It's just a matter of preference, okay, whether you want one flip-flop over the other. Okay. Okay, can you help to bridge the gap between clocks used in sequential circuits and synchronization of instructions in MIPS and DC update? Okay, so in a sense, okay, if you look back at your MIPS, Okay, what you have covered so far. This whole idea of a clock, where is it? Okay, where is it? Does anybody know where is the clock here? All right. So the main clock, all right, that will sort of trigger the whole thing actually is here. Why? Because that is a starting point. All right. Whenever I have a new instruction, okay, it will trigger. All right. But of course, it is also tied. This this clock is also tied together with your program counter as well. So it's not a single clock tied to just one device, but it's the same clock that could be tied to many devices at the same time. All right. Okay. So it is a matter of how the whole thing works. Okay. So if you think about it, your program counter will always provide me with the updated address, correct, on where to fetch the next instruction. But when do I fetch the next instruction? I only must fetch the next instruction when the clock comes in. All right. So if you think about the time that you have, so when the clock comes in, let's say it's a positive edge, okay, I will have to wait until the next clock cycle to get the new. So if this is my current PC value, the moment the current instruction has been fetched, okay, this is a combinational circuit here. All right. That means I would have already generated the PC plus 4 maybe somewhere here. All right. Okay. And of course, having said that, you still need to wait for your, because it could be a branch instruction, it could be a jump instruction. So I still need to wait for this entire multiplexer to give me the final value, all right, to be updated to the PC. Okay, whether it's just PC plus 4, is it add with some branch offset, or is it a jump instruction, whatever. So you can imagine that whatever happens, I just need to make sure that this final address here, okay, this address here is ready anytime before my next active edge of the clock. Okay, that is the amount of time you have. All right. So as long as it is ready before the next active edge of the clock, when this next active edge of the clock triggers my instruction memory, I would already have the updated address here. Correct? I already have the updated address here, so I know exactly, or I know for sure that I'm fetching from the correct location, which is the next instruction that is to be executed. It could be PC plus 4, it could be something else. All right, so that is where the sequential or the clock comes in. Okay, in terms of synchronization between the MIPS and the PC update. Okay, so this is actually leading up to, I think, what you're currently learning now, the pipelining, right? So the whole idea is this works, correct, but it's of course not so efficient, correct, because you waste a lot of time for the whole processor to finish one instruction before you can fetch the next instruction. So that is where the pipelining architecture, which you are currently, I think, learning now, will actually help to improve your throughput tremendously. All right, so I think that one probably we'll discuss more next session. Okay, so that is how you can relate synchronization and so on. Okay, so for the self-correcting state, I think what you need to analyze is what are the present state and the next state if you end up in a state that is currently not used. Okay, so if you, what you need to do is analyze whether for those states that are not used, all right, what is my next state? And if my next state is a valid state, then we say it's self-correcting. Okay, if it's an invalid state, then you have an issue. All right, that means you may end up in a invalid state and the system cannot get out of it. All right. Now for combinational circuit, as we saw before, those are circuits that do not uh, wait for a clock. That means as long as there's an input, you will generate a new output. Okay. So for example, your opcode decoder generating of the control signals and so on. These are all purely combinational circuits. Okay. So all these blocks are the control unit, okay, your multiplexer, your sign extension, left shift by 2, okay, your ALU, all of them in a sense do not necessarily have to wait for a clock. The moment there is an input, okay, it will trigger the circuit to generate a new output. Okay, and as we saw, every hardware has a certain amount of time that it takes to generate a new output, and as long as we are sure that it has enough time uh, to finish before the next clock cycle, then you're fine. Okay, it's a question of self-correcting circuit again. Okay, so basically, self-correcting circuit is so. For example, if you have states, okay, let's say you are having state 0, 0, 0, 0, 0, 1. Okay, so let's say with 3 inputs, okay, you have 8 states. Okay, but let's say for all of the 8 states, maybe 1, 1, 0 and 1, 1, 1 is not used. All right, it's not used. All right, so what you need to do is based on your JK, because you would have designed your circuit. Okay, so let's say this is all your input. So with all of this, you would have come up with some inputs for your flip-flop. Okay, so let's say I use JK flip-flop. So maybe JA, KA, okay, and so on. All right, so you know that okay, these are the inputs to all the flip-flops, all right, based on the states that I'm using. Okay, so what you need to do is you need to take each of this, okay, unused states. So these are all unused states, and based on the JK flip-flop sort of expression you already have, what would be the next state? That means what would be the A plus, B plus, and C plus for this? Okay, because even though it's unused, you already have connected all your JK flip-flops accordingly, all right, to make sure that they are connected in a way that when any of the use states are there, they will go to the appropriate next state. Okay, so what you want is you want to check whether if let's say if 110 is unused, but I know that based on the JK values and the connections, I already know what is the next state. Okay, so what I need to do is I need to check whether these next states are actually part of whatever that is here. Okay, so assuming that I'm using all the values from 0, 0, 0 all the way to 1, 0, 1. Okay, only this last two is not used. Then as long as the next state, okay, from an unused state is actually a used state, then you are safe. Okay, why? Because if I transition back to a used state, then I know I can still cycle back within the scope of what I want the circuit to do. Okay, but if I'm in an unused state 110 and I do not go to, let's say, any of these valid states, and I cycle back to only 110 or maybe go to 111 and 110, 111 and so on, then you do not have a self-correcting circuit. That means if it happens to go out of state, then it can permanently be stuck somewhere and never recover. Is that okay? Okay, so let's move on to the other slider question. So it's a question on the RAM design. Okay, I think there's a few questions I saw in this memory design and how do you address and so on. Okay, so let me sort of go through this design. Okay, then you can sort of understand how to come up with this whole thing. Okay, so if you look at this slide there, just now this slide. Okay, so what we want to design is 2 megabyte times 32 using 512K times 8. Okay, so what do we mean by that? Okay, so let's try to understand what is the requirement. Okay, so we want to design a memory system that is 2 megabyte times 32. So what are these numbers? Okay, so this 2 megabyte is referring to the entire address range, and this is referring to the data bus. Okay, so what is the address bus? This is the data bus. Okay, that means I want to have access to 2 mega locations, 2 megabyte worth of 2 mega locations, and each location should have a 32-bit data that is accessible to me. All right, now so the first thing is how many bits do I need? Correct. So 1 meg is okay, so 2 mega means is what? Is basically 2 times so 1K is 1024 times 1024. So 1K times 1K will give me 1 meg. Okay, so this will be 2 times 2 to the power of 10 and 2 to the power of 10. So this will be 2 to the power of 21. Okay, and the data is 8 bits. Sorry, 32 bits. Okay, now what I have is or the memory chips that I have is 512K times 8. Okay, so again, this is my data width and this is my address. Okay, so how many bits do I need? Okay, so you can break it up and say this is 512 times 1K, so 1024. Now 512, how many bits do you need? Okay, so I think there was a question how many bits. So you can just do a log. Okay, so log 512 over log 2. Okay, so you'll get is 9. So I need a total of 9 bits. Okay, to represent 512 times 1024 is 2 to the power of 10. That means I need a total of 2 to the power of 19 bits. Okay, for 512K different locations. And in this memory, I have only 8 bits of data. Okay, now let's start and do step by step. Okay, let's do step by step and see how will it look like when I just deal with just one of this chip. Okay, now if I just deal with just one of this chip over here, okay, and I build my system up from that. Okay, so I know that I need 19 address lines. Correct, I need 19 address lines to address this entire 512K location. Okay, so let's do that first. So I have A0 all the way to A18, which is 19 address lines. Again, 19 address lines. And I'm going to take that entire 90 address lines and I'm going to connect it to one memory chip. Okay, A0 to A18. Okay, now when I connect it to one memory chip, this is one 512K memory chip. Correct, this is one of this chip, and I give any address, what will I get out of this? Okay, so for memory, when I provide an address, what comes out is the data. So the data that comes out will be 8-bit data here, correct? Because that's the chip that I have. All right. So if I were to look at this memory map, okay, so if I were to draw a memory map right now, okay, so if you understand the process that I'm going through right now, subsequently you realize that actually it's very easy. Okay, the same thought process. Okay, I provide an address, I get the data. Okay, so right now my address is a 512K address. That means when I start from 0 and I go up to 512K, any address that I provide, I am going to access a particular location inside a memory, and I'm going to get the 8-bit data. Correct? I'm going to get the 8-bit data out. Okay, that's how memory works. I give you an address, you give me the data. Or I give you an address and I give you the data, you update the data in that particular address location. Okay, so that is what we have right now. If I just look at it from a single chip perspective. Okay, so now before we go on to the next step, let's come back and look at the requirement. The requirement is I want to design a 2 MAC address range with 32-bit data. Okay, so now what I have is 512K address with 8-bit data. Now let's first extend the data bus from 8-bit to 32-bit. So to extend it from 8-bit to 32-bit, all I need to do is I need to have 4 such similar chips. Okay, when I have 4 such similar chips and I connect all of them to the same address lines, that means each of them is A0 to A18, A0 to A18. Then what will I get? I will, when I provide a particular address, again, a particular provide address, I will activate all the 4 chips at the same time, correct? I'll activate all the 4 chips. So each of them is 512K chip. Okay, and for any address that I provide, okay, any 19-bit address, I will activate all 4 chips at the same time, and each chip is going to give me an 8-bit data. Okay, and what I can do is I can now say that each chip is actually providing me a different section of that 32-bit data, because a 32-bit data is basically 4 8s, correct? So I can say right now that when I give a particular address, I'm going to activate 4 memory chips at the same time, and each of the memory chips is giving me one part of that 32-bit data. Okay, so basically what's going to happen is I'm going to say that this is actually representing data from D0 to D7. This is D8 to D15. This is D16 to D23, and this is D24 to D31. So now you can see that by doing this first step, I have extended my idea of a single chip with 8-bit data to 4 chips with 32-bit data. Okay, 4 chips and 32-bit data. Because when I give a particular address, I'll activate all 4 chips at the same time, because all are connected to the same address bus, 19-bit address bus. Okay, but now I say that each of them is giving me an 8-bit data, which I will pack together as the 32-bit data. All right, so effectively, okay, I will combine all of this together to give me a 32-bit data. All right, so now what I have created something in between now. So I've created a 512K times 32. Okay, so you have come from here to here. Now what I want to do is I want to extend this to here. Now I know that if I take this entire idea, this 512K times 32, and I repeat it one more time. Let me just repeat it one more time. Okay, so I'm going to take the same design that I have, and I say I want to repeat this entire design one more time. Okay, so it's also A0 to A18, A0 to A18. Okay, and I'm going to connect this same address bus to all this second group of chips as well. Okay, and as before, each of them is also going to come up with 8-bit, and I'm going to combine them together. Okay, the same design. Okay, and this is actually connected to the same bus. They're all connected to one bus, one data bus. Okay, now if I keep this design as it is, what will happen now? When I give out an address, I'm going to activate two groups of chips at the same time, which means I'm going to create a conflict on the bus, correct? Because for the same address that I provide here, I'm going to activate this column, and then I'm also going to activate this column because they are all connected to the same address bus. Okay, but what I want to do is I want to keep one column here for 0 to 512K, and I want the next column is from 512K to 1024K. That means the next 512K. All right. So what I need to do, I need to be able to switch between the first column of chips to the second column of chips. All right. So that is where I'm going to use the remaining bit. So I know that I have a total of 21 address lines coming out. Okay, to access the full 2 meg range. And since I'm already using 19, I have another 2 more bits left. So what I'm going to do is the other 2 bits, which I'm currently not using, A19 and A20, I'm going to connect to a decoder such that I'm going to activate 4 lines because 2 to 4 decoder, correct? So if it is 0, 0, then I say line 0 is activated. And I connect that to the enable. Okay, this is the enable of each of these chip here. Okay, so when A19 and A20 are both 0, 0, okay, so maybe I should put the other way here around. Okay, so when they're both 0, 0, then I'm actually accessing this range. So this is line 0. Okay, when I switch to line 1, 0, 1, I'm connecting it here, and I connect this to the enable of the other column. So when it's 0, 1, what happened? That means I have moved from the lower 512K to the upper 512K. This is line 1. Which means that now there is no longer a conflict on the bus, because when my upper 2 bits are 0, 0, line 0 is activated. So I use that line 0 to activate the first column, which is the first 512K. Next, when it's 0, 1, the next column is activated, which is the next 512K, and then 1, 0, and then 1, 1. Okay, so I just repeat this entire process another 2 more times. Okay, that means total 4 columns, and each column would activate one 512K block, and each of them have 32 bits. Okay, so that is the idea, okay, behind this design that you see here. Okay, so I think that sort of covers all these questions here. Okay, how to know the bits and how to calculate the address and so on. Okay, so you just remember that the idea is always the same. You always use the lower bits as a common across multiple memory chips, and use the higher level bits to differentiate different groups of components or memory chips in this case. Okay, the idea is always the same. You always keep the lower bits, in this case A0 to A18, the lower bits as common across all the components, and use the higher bits, in this case A19, A20, to select the correct chip that you want, okay, to talk to. Okay, so that is this. Okay, any questions on this? Okay, so let me move on to the extra questions here. Okay, so the extra question here is implement a sequential logic circuit that cycles through the following states using only JK flip-flop. Okay, so I think it is quite similar, okay, to what we have been doing all the while. All right, so you can see 0, 0, 1, 1, 0, 0, 1, 0, and so on. Okay, so the process is the same, correct? Okay, we have the current state is 0, the next state which is already given in the state transition diagram, and then based on the excitation table, we just fill in JA, KA, JB, KB. Okay, so in this case, you can see that we choose values that make life easier for us. Right? So in this case, JA is 11XX, KA is XX11. So since it is XX, we can just assume that we assume the X to be 1. Okay, for JB and KB, we can just assume that this X is 0. So this is 1 and this is 1. So it always follows your A value. So JB and KB both you can say is tied to A. Okay, when A is 1, then JB is 1 and KB is 1. Okay, so that's how you get this. All right, so it's in a sense showing the same process as we saw earlier. All right, the same thing. So I will not go through step by step. Right, the same thing. Okay, so for next question here, okay, we asked to study the sequential circuit. Okay, which uses 4D flip-flop. Okay, and we are asked to look at how many states there are. Okay, so in this case we have a clear button. So this is what I mentioned just now, where this sort of acts as a reset button. Correct? That means you can ensure that you have a preset starting point, okay, by activating this particular signal here. So when I clear, I will always start at 0, 0, 0, 0. Correct? Now you can see that for the last flip-flop, the Q bar is connected back. So if the last output is 0, then Q bar is 1, which will be connected back. So this 0 will flip to 1, the Q bar, and come back here. So in the next clock cycle, what I will see is 1, 0, 0, 0. All right, and then the same thing will happen. This 0 will flip and come back, and everything will shift. So it's like a shift right, okay, while the last bit is flip and come back to the front. So it'll become 1, 1, 0, 0, then 1, 1, 1, 0. Okay, then 1, 1, 1, 1. Okay, after that it will become the last bit is already 1, so if it becomes 0. So 0, 1, 1, 1, then 0, 0, 1, 1, 0, 0, 0, 1, and then 0, 0, 0, 0. Okay, so this and this are the same. Okay, so total is 1, 2, 3, 4, 5, 6, 7, 8. So total is 8 states. Okay, so total you have 8 states in this system here. Okay, so next we are asked to come up with the expression, okay, for each of the state. So here we are told that state 0 is when we are in state 0 here. This 0 is referring to 0, 0, 0, 0. Okay, the starting point. Okay, so that's the state 0 here. That's what is state. And the next state is state 1. So this is basically state 0, state 1, state 2, and so on. Okay, so what they asked to do is the simplest Boolean expression for state 1 and state 2. Okay, so the simplest Boolean expression would be because there is always only one unique combination of a particular bit being 1 and the next bit beside it being 0. Okay, so for example, if I look down here, I can say this is A is 1 and B is 0. Here is B is 1 and C is 0. Here is C is 1, D is 0, and so on. Okay, now that is okay one way in which you can answer. You can say it's A B bar or B C bar and so on. Okay, the other way is you can actually also do a K-map. Okay, if you want, you can also do a K-map and solve this. Okay, so if I were to do a K-map for state 1, for example. Okay, so let me put it here. Okay, so this is for state 1. So this would be AB and CD. Okay, so we can say that for state 1, only this is output is 1, correct? 1 0 0 0. So 1 0 0 0 is it. So this is the only one. Now then we need to fill in the x's and the zeros, correct? So we can see that 1 0 0 1 is not there, so it's x. 1 0 1 1 is a x. Okay, 1 0 1 0 is also x. 1 1 0 0 is 0. Okay, so in this case only state 1 is a 1, and state 1 is only one combination, which is 1 0 0 0. So all the other possible states will be 0. Okay, we're not interested in that. Okay, when we are doing the K-map for state 1. So 1 1 0 1 1 1 0 1 is not there, so this is x. 1 1 1 1 is there, so it's a 0. 1 1 1 0 is also there, so it's a 0. Okay, so we also want to see whether on the top row there is anything, all right, where any access that we can use. All right, so we will see that 0 0 0 0 is there, so it's a 0. 0 0 0 1 is also there, so it's a 0. Okay, 0 0 1 1 is also there, so it's a 0, and 0 0 1 0 is not there, so it's x. Okay, so this second row we don't need to worry so much, because that is not going to help us in any of the K-map reduction. Okay, so based on this, you can see that the only possible grouping that I can get, okay, would be this. Okay, which will give me A and B bar. Okay, so you can do the same thing for state 2 and you also get the same answer, B and C bar. All right, so the important thing is in each of these state, only that particular combination is the 1. Okay, everything else is either 0 or x, and then from there you can sort of group it and get the most simplified expression. Okay, so that brings us to the end of all the questions for discussion. Yeah, so if any other questions you have, you want to discuss, I will stay on the line. If not, that's all we have for today. All right, so thank you. Yeah, so I'll stay on the call for any other questions you have. Okay, why did I only circle the last row? Because that is the most simplified expression you can get, correct? You can't group that one with anything else. This is the part A. question one from the very first question, is it? Or this? Okay. I mean, to draw. There is no drawing here, right? It's only the circuit. I mean, even if you're asked to draw, it is just simple like OR gates and NOT gates only, correct? That is, if you were asked to draw, you just say that, you know, TA X bar, you know, like that. And TB, you just take the yeah. So I'm not very sure whether it's asked to draw, but okay, I mean, if you asked to draw, you just it's a simple expression, correct? X bar will be TA, and AX nor with X will be TB. The extra questions, is it? Extra questions is okay. I mean, even if you're asked to draw this, it is just straightforward in the sense that you have two flip-flops, correct? So yeah, JA, KA. So in this case, both of them tied to a 1. And JB, KB. Both of them tied to A. So this is your A output. This is your Q bar. So this is your A flip-flop, and this is your B flip-flop. And this is tied here to here. So this is basically your A plus, A, B plus. Yeah, I mean, yeah, you still need the clock, you know, right? So a complete circuit, you still need the clock. Okay, so any other questions? Okay, so that's all. Thank you. I'll see you next week. Okay, bye.